So can I have one little rant about user interfaces and our Canvas tool? Well, it lets you easily mess stuff up. So there's a couple of, just for reference sake.
Oh, it's so easy that easy to mess up.
Well, it's not even all that easy, to be totally frank.
There's nothing but bad things about the backside of Canvas.
Yeah, I'd like to kick the backside of Canvas. Yeah, so and when I was making exams, one of the things that you cannot do in Canvas that I would think, like anybody, if anybody at Canvas had ever been in a classroom and taken a course somewhere, I would think they would conclude that, oh, if the teacher made a typographical error in selecting which of these multiple choice answers is the correct one, that even after students submitted their exams and went, oh, no, it was supposed to be C, and most of the students picked C, and Canvas marked it wrong, but I want to go back and choose B. Can't do that. You can't go back and say the real correct answer was this. And I don't know how many times it's got this little subtle problem that if you, I'm not sure what key press it is. It's an obvious one. I've done it half a dozen times where in an exam, like adding elements to the exam, and you press obvious enter, and it's there, and then you say save, and it's not there.
Oh my God.
Just gone. Just occasionally, just every once in a while, enough, right? One of the keys to good software reviews is make the errors in your software infrequent enough that the user thinks it's themselves that caused the problem. So they've got to have people on that all the time. All right, I'll stop.
Quality software.
Well, there's a few obvious things, like regrade a test. Like, how many times has a teacher ever made a typographical error on which is the right answer, right? I mean, it'd be like, oh, one more rant. Can I have one more rant? I'm just venting. It's getting it off my chest. I'll be a better teacher for it. When you go to their website, when you go to their big quotes, I never use air quotes except when something is so stupid. Help desk. I've probably half a dozen times gotten an answer that says, no, we don't do that, but we suggest that you fill out, click this link to add it to our list of desired features. It's like, okay.
Anyway, computational time complexity.
Computational time complexity, yes, that's where we are. Okay, so what we are trying to come up with is a measure of how much work has to be done, and we're leaving it somewhat right. It's machine independent, so we're not saying, okay, this is going to take this many milliseconds or microseconds or this many clock cycles or anything. So we're using a little bit of vagueness intentionally and trying to come up with, we'll look at things like how many comparisons have to be done or how many steps have to be done relative to the number of inputs that we have. And so I want to define more completely the big O notation that we started looking at. But to give kind of a, let's just give a and something like this. And let's just say, so this is a sequence of instructions. And what we're trying to, I want to do first, like the real calculation of like how many steps are here, and then we'll look at what we're trying to do with our big O notation. Yes.
So the other for loop is outside the two for loop?
Yes, it's not listed in, nested inside. It's
Okay.
sequential. So what we want to do is just add up kind of the number of steps relative to n. And we could have, let's throw in a WW. So this is just crazy function calls that we're doing. So if we were just doing a, let's look at the, or a word, let's call it the detailed analysis. Let's say we have measured, we know this takes 25 milliseconds to execute. Let's say this is 25 milliseconds, and this is maybe 100. Okay, so these are, I'm looking first at a detailed analysis that would be, right, as soon as I do this, I'm saying it's dependent on some machine and operating system and compiler, and as soon as I put hard numbers on that, I'm saying we're trying to get a detailed analysis. So if we're trying to find this, what I want to come up with is an expression based on n that will tell what the total elapsed time is, right, based on n. So it's going to be, the result is going to be a polynomial with n as the variable, right? Remember, oh no, what's a polynomial? Probably ought to refresh that. What is a polynomial? Yeah, ballpark.
It's it's a series of.
It's an expression, I think, with terms put together with like addition, subtraction, multiplication, and exponents.
Yeah, that's good enough for our, we don't need the math definition. Essentially, we want to come up with, it's going to be an expression in terms of usually, for our purposes, right? Sorry, any math majors, it's the, pull this out of the archives in 2195 of the rubble of our civilization, and find this,
Oh,
say, what is this guy talking about?
well, that's.
So we're looking for a polynomial that is an expression in terms of powers of a variable. And we usually write them in decreasing degree of the variable. So it might be n to the fourth, n to the third, n to the second, and it's got coefficients. So it's going to be something of the form, right, where we have like a coefficient and these coefficients can be positive or negative. Just so we could put pluses between them, all right? Plus a negative coefficient, whatever. Down to a C, let me think. Can we get it right? Get down to 1 through n. We all have C sub n. It's good. That comes up to n. That comes down n to the 1. Plus some constant at the end, right, that we can add on. And we usually write them in decreasing. The degree of that term is what power we're raising the variable to. Oops, 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 oops. Sorry. I switched variables on you right now. And then we can add a constant on the end that doesn't have a variable. So hopefully it looks kind of evident that we could come up with something like that out of this. How many times is this going to be executed?
5n squared.
5n times n, right? So nested loops are multiplicative. So this would happen 5n squared times 25. Our units are, that's how many milliseconds this would take. Plus, what's this going to be? Yeah, we're actually going to, let's see, get that off by one error out of our system. It's going to do inclusive. Looks good. Times 225. And then this is just a constant, right? This is just. So if we put that into a polynomial shape over here, we'd have something like, take this, right? Let's see if we multiply that. Should have picked easier numbers. That's 900. What's that? Did I lose you on where we're going? So we're just writing the total time over here. Total time to process. And we're leaving off, right? Because just so in case you're extremely literal, the execution of each one of these loops is going to cost a few machine cycles, right? But we're saying inside here, are these we're neglecting that as some overhead that we don't really care about, because presumably this method call here, 25 milliseconds, would be so much greater than a little bit of overhead of incrementing a loop counter in there, right? So we're trying to get an estimate. Okay, so 225 times 4 looks like 900. And then we've got 2025, yes. Okay, so that's a negative. And we've got a plus 100. Wait a minute, Al, what are you doing? Where did these negative 2025 milliseconds come from?
The -9.
Yeah. So do we have a time machine? How in the world are we doing negative milliseconds here? This is just to keep you from, waking up in the middle of the night going, where did we get the negative milliseconds from?
Yeah.
What are those actual? I mean,
Well,
they're not negative milliseconds, right? What are they?
It's just how many milliseconds should not be counted from the 900 end.
Yeah, exactly. Right. They're because we didn't start at 1 here. So we got the total of, if we had done that, minus what we didn't do. So they're not like a weird time warp or something. So we can, if we pull, or we add the 100 onto there, we make that a 1925. Okay, and that's just residual. That's we're trying to get the total of how much time is the whole thing going to take, and this is the part that the 900 would take a certain amount of time, and we didn't do all of those, so we're coming out. So we have to subtract that part off the constant. All right. So here we have a polynomial, just like we wanted. And now let's talk about, so here's our detailed analysis that perhaps the computer engineer would say, look at all the stuff you're leaving off, right? But because we're saying these happen instantly, but we're trying to look for the significant elements that are like these guys, right? That take some significant measurable amount of time. So big O analysis classifies problems, classifies algorithms, I guess I should say. So we're going to look for what we're trying to get is the big shape of how long does this thing take? And what we're going to say, and I should add on here, as n gets big. And what we find is if I have an n squared curve over here, what is this thing going to do? Right. Well, this has 125 n squared, so what would that do to our values? We've got a multiplier on, this is just n squared by itself, say. And this is big N. And so N is large out here. Well, 125 is going to do what to, if I have the n squared function here and then 125 n squared, what are they going, how are they going to look? What's the 125 going to do to that? Shift it up, shift it down, stretch it out. So constant would move it up, right? But it's going to make, so every place where this is coming up, and we have no scale, right? So that's okay. So my, it's not supposed to be wavy. All right, 125 n squared is going to go up faster. But it's going to, in a sense, parallel the n squared function. And as n gets really big, the n squared portion of that is going to take more and more priority over the coefficient we have on the front. What does adding the 900n on there do? Well, that's going to make it, again with no scale numbers here, that's going to make it go up. It's still going to, in a sense, parallel largely that. And then our minus 1925, what would that do? That would pull the whole thing down. So we might have values that are, well, it would be less than the second one. Anyway, what I'm trying to get at here is that the overall shape of these is going to be very similar. The bigger n gets, the more they will approach the curve represented by n squared. So big O, so this is looking for worst case. We're looking for something that's an upper bound, such that, over on the other board, if this is my, say, t of n, my function, my time function, this is my function by which I calculate the execution time. So as n changes, we expect my number, my total processing time to be related to the square of that plus that minus the constant, right? So big O finds a function let's see, I want to say f of n All right, so here's our, I don't believe this is exactly, I'm sure it's not in the book exactly this way in your textbook. But this is a nice way to picture, and I think it brings up, clarifies what it is that we're trying to do. We can prove mathematically that if I choose the highest if I pick the highest degree term in my polynomial that's expressing my time, then this will necessarily be true. So we could solve, for example, we could solve for a C1 and C2. And some with the C1, C2 values that exist, right? So we could solve for a C1. We would guess that our C1 would be greater than 125 since we're adding on 900n as n gets big. This is going to become very insignificant as n gets larger. But notice whenever I'm adding after, say, n gets to be 900, this would be another, if n were 900, then this would look like 126 n squared. Catch that little sleight of hand, right? If n were 900, this would be another n squared in this case. So a value that is 126 times n squared would be greater or equal to that 125 n squared plus 900 times n if n were 900. So I'm trying to get your buy-in on the plausibility that there would be, as long as I take the largest degree of n, I can throw a multiplier on it that will always be greater than whatever expression I have in terms of that highest order n plus any collection of lower degrees of n. So if I had an n cubed out here, I could put a constant on the front of that n cubed, and it would eventually, for some n, I could find a constant for which my n cubed would always be greater than this polynomial in n cubed. So all that's to justify the next crazy thing that we're going to say in determining what the big O value is. So we're purposely, what are we trying to do? We're trying to categorize algorithms based on simple powers of n to begin with. And to say this whole big thing is actually going to reduce down to, we're going to say that this is big O of n squared. Even though there are other terms of lower powers of n, we can classify this, and as n gets big, what we can say is that this will run in the same class of problems solving the same problem, same solution as other problems that run relative to n squared. And so when it comes down to comparing algorithms, for example, even though the algorithms might be very different, if they both fall into, say, n squared time, if they both have a big O of n squared, we can say they are roughly equivalent and comparable to each other, and in fact, almost indiscernible from each other as far as their execution time. Then I start talking about, well, here's an n squared problem, here's an n cubed solution to the same problem. Which one is better? Well, clearly the n squared will run much faster. And I can, in the world of sorting, we talked about last time, I threw up the bubble sort and selection sort are both n squared, but quick sort, heap sort, merge sort are all n log n. Well, n log n is an improvement over n squared, and so substantially so. As n increases, the log of n goes up much slower, and becomes much faster as n squared goes up at a high rate, and log n goes up at a much slower increasing rate. So here's our key point, is that big O is considered of a function is considered an upper bound or worst case, as long as we can find multipliers that can bracket, go around the actual function. So what we're trying to do is condense down, reduce that. So if this represents, and it's a very simple example, right? But if this represents the real time calculation that we could do, then what we're distilling that down to is to say, well, the really important part is the highest degree power of n in here. And what we're going to do, disturbingly, right? We choose the highest degree as the function, and we're going to omit coefficients and constants. And so we're not going to look, we're never going to have, other than in a quick illustrative sense, we're not going to have O of 5n squared, right? That would just become n squared. We throw away the coefficients, we throw away the constants, and if that sounds like, wait a minute, that's just crazy, you're just changing the number, you're changing the function, right? Well, look at the definition. We can always find a constant we can multiply by. Now, this would not hold. I could not call something that had n cubed here order n squared. Why? Because anytime I throw a constant on there, eventually, all you have to do is imagine what I just did over here. If I had 125 n squared, when n gets to 125, right, then it looks like n cubed. And where was I going with that? Oh, that the n cubed, if there's an n cubed term in here, we can always, no matter what constant we pick, if we go a little bit bigger on n, it will break through the upper bound that we tried to establish. So that means that higher powers of n are going to increase substantially faster. So with that kind of set up for what are we going to look for? We're going to look for what's the highest element of the time function. And we're going to say we don't need the coefficients for what we're trying to do. The coefficients are going to change slightly the shape of the curve, but they're going to change the rate of growth here, but they'll still be following along based on the power of that n is being raised to. So if we give a summarize some of these different functions, there's a few that we see all the time. If we look kind of the standard, we look at time versus number of elements. Okay, so that's processing time. Well, we've got a, we kind of mentioned last time. This is a linear function of n. We're throwing away coefficients. What would a coefficient on the front of a line like this? First of all, this means that f of n equals some constant times n plus, I'll call it C1, C2, right? A linear function, the highest power of n is just 1. And so what does that do for you? If I double the number of elements, what happens to my processing time? In a linear function, it's going to double processing time. So it's proportional, right? So no matter how far you get here on big values of n, you're still going to have, if you go twice as far out, it's going to take twice as long. Think of, follow the line up to here, follow the line up to here, and that ratio, that proportion is going to hold out anywhere. But now what does C1 do? What does that multiplier do to the curve, not much of a curve, it's a line, but to that function? How would it alter it? Yeah, it's going to change the slope, tilting it, right? It's still, where the shape of it, it's still going to be a line. It's just going to be a line with a different angle. But that still means that everything will be proportional. It'll just go up faster, but you can still count on, if you move twice as far out, it's going to go twice as far up on the other thing, on the vertical axis, the other thing. So this changes the slope. And what does this do? Yeah, it's going to move it up, or if it's negative, it'll move it down, right? So we're changing the angle, or we're possibly moving up and down, but what's not changing is the fact that it's still a line. And that's determined by the power of n that's in here. So what we're saying over all that, we're saying we can throw away the coefficients and throw away the constants because the relationship as n gets large is going to be linear, and that doesn't matter. We're more interested that it's linear versus n squared, n cubed, another power of n. So if we go up by 1, I'll try to draw. This is going to be a function based on the square of n. What will
Quadratic.
quadratic? Yes. Oops, not quadratic. So it's going to be a quadratic function. You should know those two terms. And a squared term is called a quadratic function. A n to the 1 is a linear function. I think those are the only common names that pop up in our usage.
How about logarithmic?
Oh yeah, yeah. That's actually the next thing I was going to is, what does logarithm look like? Well, it's not an inverted parabola, and it shouldn't go down. It's kind of hard to draw. It doesn't have wiggles in it. But if this were it's going to be always increasing, right? But as n goes up, the rate of increase actually goes down. So it's going to go up by less than it did earlier at smaller values of n. What base are we talking about? Usually, for algorithmic stuff in computer science, we are fond of splitting things in half using binary trees, splitting the upper half and the lower half of a data set. And so we often use log 2, and that's what you'll see that the best sort methods are order n log 2 of n. But it actually, because logarithms are goofy, that's a mathematical term. No, that's a computer science term. The base of the logarithm, how does it change the value of the logarithm? It changes it by a multiplier, right? So it's just a coefficient, essentially, on the log. So guess what? Coefficients go away. So because coefficients go away, the base of the logarithm also goes away. So why can we do that? Well, the basic shape of the logarithmic curve is the same regardless of your base of your logarithm. For R, right, if there's mathematicians having cardiac events over that. I'll throw on the disclaimer that for computer science purposes, that covers everything. So these are our obvious right, logarithmic curve. And basic powers in cubed, right? Go something like that. But then there's some really crazy ones. Yes. And we don't have a scale here, but let's, so it won't really do justice, but if you look at a table, I should, I've got one around for illustration. Things like, it won't do it justice. N factorial goes up crazily. 2 to the n goes up really fast, and I can't even do anything, but something like n to the n, imagine, goes up really, really fast. So we can actually, I wanted to write a little, we'll make a little table of those guys just to show how radical they are. And I want to stress another important element from a practical standpoint when we're trying to do these comparisons. There's
Yeah, my calculator does not want to graph a n factorial.
not even for a little n.
Much, man, it's too much.
I mean, isn't it impossible to calculate beyond like 53 factorial? Or
Oh,
something
no,
like
it's
that?
possible, it just takes a really,
Yeah,
really
it just
long time.
takes a while. Right, right. Yeah. The you may remember the
Oh, there's a limit, 69.
so it found 69 factorial?
Yes. And then I'd stop at 70.
Obligatory, nice.
I believe we'll get in the ballpark here, figure it. Are you familiar with the somewhere you can't get your computer science degree without having seen Towers of Hanoi problem? Okay, you're gonna go, yeah, if I can't get my degree, I think I've seen it. Towers of Hanoi problem concerns. We actually
Are we learning in this class or an algorithm?
both.
Okay.
Yeah, you say Towers of Hanoi a lot.
Now we're gonna touch on it here. We'll probably hit it once for reference in algorithms, but we actually, when my first child was born, I didn't realize it, but we received as a gift the Towers of Hanoi toy. It's a little like Fisher Price thing with a peg in the middle and these little round donuts, smaller and smaller rings. It's like, I know where that is, what that is. I tried to teach her, but at that point, all she would say is like, no, this is the Towers of Hanoi. Look, no, you can't put them that way. Can't put the bigger one on the smaller one. So the Towers of Hanoi consists of a set of discs. Let's see, do I want? Yeah, I'm done with that. Where'd my eraser go? Okay. It's okay. So real quick. For something that looks really simple, classic problem, there are 3 stakes and a set of disks and 1, 2, 3, we have an intermediate and a goal. Move disks from post 1.
Oh, it's that ring puzzle from Knights of the Old Republic.
And you see it everywhere, including there.
And the constraint is cannot put larger disk on smaller one. I have to see if I had still somewhere in the crawl space. There's got to be a Towers of Hanoi toy. So the process would be I can't move A, B, C, D. Just for quick reference, I can't put A directly over here, right? Because I get a I can't put anything on top of it if I do that. So what I have to do is, and they're stacked, so I have to take them off. So I have to do something like move A over here, then move B over here, then I can move A over here, and then I can take C off and move it over here. And I don't recall exactly. Anyway, you have to move the disks around a bunch of times in order to get them so you can finally end up with E, C, B, A all sitting over here, based on the rule that you can't ever put a large one on top of a smaller one. Right, so you have to keep moving back and forth. And that's an n factorial process. The number of steps that you have to take to do that is n factorial. Well, just to give a sense of what that means, for n equals 64, let's see, what did you got it to go to 69? Would you know what the number was? What you got for?
It was a big one.
So
1.71 times 10 to 98.
Yeah. Pretty big number. I believe you can do this yourself because you're all certified computer science people. If you do something like 1 million, it's 1 million operations per second. Move 1 million disks per second. It still takes like 5 trillion years to complete it. So um, often people naively will look at a problem like that and missing, well, one of the takeaway concepts here is when you have something like this, it's intractable, which means practically unsolvable for very large n. And you can't do anything about it. That's kind of the horrible truth is, so if it takes 2 trillion years, 3 trillion years, whatever, it's almost like the national budget, right? 2 trillion, 5 trillion, 18 trillion, whatever, we got paper. We can print it. Stop it now. Suppose you can double your processor speed. Okay, now it's only 1.5 trillion years. Great. What happens if I say, no, I don't want 64, I want 65 disks?
You shouldn't have said that.
Okay, so yeah, your double processing time, processor speed had no effect, right? So the idea is that when you get into an intractable function, all you have to do is typically increment n by 1, and if you somehow could solve it for n, or you came up with a fast enough machine, incrementing n by 1 blows it out of the water, and you can't solve it again. So that's the big takeaway from the idea of what the shape of that curve looks like. If we look at, where are we at? What's a couple of quick, let's lay down real fast, just little table n, n squared, let's do n factorial, I think we can whip these out. So for n equal to 1, these actually become kind of easy. N squared is 1, n factorial is 1, 2 to the n is 2, n to the n is 1. What about 5? 25, n factorial, 2 to the 5th. And n to the n, well, for 5, it's 5 to the 5. Oops. 125.
$3,125.
I'll take that. That was on the tip of my tongue. So interesting. Notice you might be deceived into thinking n factorial is way worse than 2 to the n, and even n to the n takes off really fast, right? So hard to mistake that. Can we do 7? Goes up to 49. 7 factorial. 50, 40. Okay. 2 to the 7th is only Like 7th is 1 less than. And, ooh, 7 to the 7?
123,543.
Pretty big. And let's wrap it up with 10 here. That's easy, 100. That doesn't look too bad, right? Now when we hold it up next to other stuff, right, our frame of reference is always kind of what you're comparing something to. N factorial?
3.6 million.
That's pretty close. What about 2 to the 10? I'd have that stored in your memory banks. Supposed to be 1024. And I don't know, 10 n to the n for 10, 10 to the 10. Oh.
About to say,
How does that?
anything scientifically.
I did that one in my head. So you can see by comparison, if you throw an n cubed column in here, it wouldn't touch any of these. But an interesting observation, we'll stop there, is it looks like, well, n factorial is faster than 2 to the n. If I'm going to go for small numbers, actually here, and we skipped some of the interesting area where the fast growing things like n factorial doesn't look that big compared to n squared or n cubed until you get to about 5. And even this 5, I guess it's at 6. 6n squared and or 5. Anyway, in here, there's some places where the really fast growing functions don't look like they're growing as fast as these guys, like n squared or n cubed. And so it can be deceptive, right? If you're measuring, and you might conclude for very small numbers of n, well, this doesn't look too bad. It's maybe it's only an n squared function, and in reality, as soon as you get very large n's, you might discover that your algorithm is actually one of the horrible intractable value functions. All right, we'll stop there. We'll pick up Monday for us, and if this is the end of your week, have a good weekend.